and I'll tell you what I mean by that, or at least as much as I know of what I mean by that. Okay, so let me just start with the first example, which is if we consider imaginary quadratic fields, so degree 2 extensions of the rational numbers. So these are all k equals q adjoin the square root of minus d for some positive square-free integer d. So each of these quadratic fields has a class group, a finite abelian group. I'll write it class group of k sub k. That controls a lot of the arithmetic of the number field. So it's some finite abelian group. And to be even more concrete, for each prime p, so if p here is a prime, then I can look at the p-torsion in the class group. So these are the elements whose pth power, if you're thinking multiplicatively, or when you multiply by p, if you write it additively, is the identity. So this is just this is always just a vector space. You know, this is maybe I'll write it z mod pz to the to some dimension. So for each imaginary quadratic field, there's a class group. It has a p-torsion, which is just a finite dimensional vector space over z mod pz as some dimension. And so one of the motivating questions of the kind of thing that I'm going to be talking about is how does this p-torsion in the class group, which if you want, you can just think of actually as a number, the dimension of the vector space, since that's all you really can say about the p-torsion. So how does this behave as k varies? Okay, so if I look over all k, how often is this p-torsion 0-dimensional, 1-dimensional, 2-dimensional? That's the kind of question. And I like to actually use the language of thinking about it as a random variable which depends on a random k. So maybe, or so if you have some notion of a random k, then this is some random variable that depends on it. And you can ask, well, what kind of random variable that is. And you could ask, for example, what's the average size of the p-torsion? So, what is, so then I like to say for a random case, because then I'm going to use expectation for the average size. So what's the expectation or the average size of the p-torsion in the class group? Or if you're going to ask about the average, you could also ask about any of the higher moments. So what's say the average size of the kth power of the p-torsion? Okay, so I will say once here what I actually mean by that, since I haven't really said what a random k is. So when I write something like this, when I'm talking about the average, when people have studied this, what we usually mean is if I had only finitely many k, I could use a uniform random k, and we're going to do that and take some sort of limit. So what this really means, the definition of this, so this is the limit as x goes to infinity of the average over the first however many imaginary quadratic fields. And so what is the first however many imaginary quadratic fields? This requires you to order the imaginary quadratic fields. And we order them by discriminant. You could, it's usually the only way anyone orders imaginary quadratic fields. So there's another natural way, I suppose. You could order them by the square-free d's. That's slightly different. But this is going to come up later, because eventually I'm going to be talking about fields that aren't just quadratic fields. And then the question of how to order them there become more options. But for now, so we'll average over imaginary quadratic fields of discriminant, of absolute discriminant at most x. So there's only finitely many of those, but eventually as x goes to infinity, we're going to get all of them. And then what are we going to average? Well, we're averaging, so this same thing up here, the same k over q's, and then we'll say average the pth power of the size. So that's what I mean by that moment. Okay, so, well, there's a couple of things we know about this question, and so one of them is that genus theory tells us actually we can understand the two-torsion in class groups very explicitly. So the two-torsion in the class group, the dimension there is basically the number of ramified primes or primes dividing the discriminant minus 1. So this is the number of ramified primes of k minus 1. And so then that becomes a pretty concrete thing. I mean, it's essentially asking, up to some issues at 2, asking about if we look through square-free numbers, what does the distribution of the number of prime factors look like? And that's a very classical kind of thing. And that actually then implies that all of these moments are infinite. Okay, so that actually doesn't feel like it gives you great information. On the other hand, so that's for p equals 2. On the other hand, the Cohen-Lindster heuristics, which are it's a conjecture from 1984 by Cohen and Lindster, which say how the rest of the class group should act, the odd part of the class group of quadratic field should act. They conjecture here that for p odd, for example, the average size of the p-torsion, the first moment, is 2. Okay, so they conjecture that for p odd, the average size is 2. And notice that 2 didn't depend on p. And we know this conjecture only in one case, which is the theorem is that due to Davenport and Heilbronn from 71, that the average of the 3 torsion is indeed 2. But we don't know this for any other p, and we don't know any other moments as I've written them here. But we expect this is true. There's a lot of good evidence. I believe this. There's a lot of things in this field where we aren't sure what to believe, but you should believe this conjecture here. And the thing that I want to emphasize, which is from the title of the talk, is that here 2 is bad, and that odd p are good. All right, well, it's not exactly clear yet what good and bad should mean, but the point is that 2 behaves differently than all the other primes, and all the other primes we think behave quite uniformly. Right? They all somehow, I mean, this 2 is the same for all the primes. And in fact, well, I'll say a little more, but that somehow all the other primes, the p-torsion in the class group is acting in a kind of uniform way, but 2 has got a totally different thing going on. And that makes sense here because we have genus theory to tell us about the 2 torsion in the class group, and we know absolutely nothing else about the rest of the class group. So let me just say that the fact here that the average is 2 is perhaps like a little bit misleading, but not too much. Let me just say that if instead of imaginary quadratic fields, we had considered real quadratic fields, we would still have that all of the moments of the 2-part are infinite. It's a little more subtle because you have the narrow class group, but it's not that bad. So we still have that all of the moments are infinite of the 2-torsion, but here the conjecture of Cohen and Lenstra is that for odd p, that this is 1 plus 1 over p. So it does depend on p, but it depends on p in this sort of uniform way. And one could formulate more on the level of the distributions of groups, more what that uniformly means. But one concrete shadow of that uniformity is that this is, for example, a polynomial in p and 1 over p that you get for all the p's except for 2. Okay? And this, again, is known when p equals 3 from Davenport-Heilbronn. And all of the higher moments for p odd are conjectured to be, for each moment, there's a polynomial in p and 1 over p. And we'll get more into what it is, and they're very sort of concrete. But all the other primes behave uniformly, we think, for quadratic fields. So the question that I've been thinking about is if we replace these quadratic extensions, our k over q quadratic, with higher degree extensions, which p are bad versus good. So somehow, in retrospect, it all seems so obvious that 2 should be bad and everything else is good in the quadratic case, but I think it is not at all clear for any higher degree examples which parts of the class group somehow misbehave. So Cohen and Martinet in 1990, they generalized the Cohen-Lenstra heuristics from quadratic to arbitrary degree. And in fact, this is where this language of calling some of the primes bad and some of the primes good came forth. So they made a prediction on sort of this good versus bad issue. But I think that they would even agree that the prediction, it came out of the machinery they were using to build the heuristics, to build certain kinds of measures on, finite groups with certain actions. And their machine, to produce the heuristics, which has absolutely nothing to do with class groups, it broke down for certain primes. And they said those primes were bad. But it wasn't anything, the reasons had nothing to do with class groups or number fields. But let's just say, for example, for cubics, so for k over q degree 3, they would say, they thought that all the primes other than 3 would be good, and that 3 would be bad. And this is actually like the beginning of a great story. So then 4 years later, in 1994, they had been looking at data that people had produced of class groups of cubic fields, and they wrote a paper called "Some Good Primes Are Not So Good." And they thought that maybe 2 would be bad. Now looking at whether the data agreed with predictions, and so let me just give a concrete conjecture. Since what I'm saying good and bad, let me turn this into actual mathematics. So here's an example conjecture of Cohen-Martinet. So for k totally real cubic, they think that they thought that the average size of the p-torsion should be 1 plus 1 over p squared. So again, this is a sort of uniform description, this polynomial in 1 over p. So they originally conjectured this for p not equal to 3, and then later maybe you would say they conjectured that also p should not equal 2 after their paper, Some Good Primes Are Not So Good. But then Moduli proved, I guess probably I wrote 05 here, but this was probably in your thesis, and then eventually came out in the paper. So that would have been in 01 that for p equals 2, the p equals 2 case is true. So it looked like maybe maybe 2 was good. And I should say that since then there have also been some reasons to think that 3 might be good. Okay, so there have been some arguments that 3 might actually be good. Let me mention one other important development before I get to in the sort of history of. And so here, I mean, I'm going to keep saying good and bad, and it sounds a little mysterious. I mean, it really needs to mean something a little higher level structurally at the distribution of groups. But if nothing else, minimum, it should mean, like, is this kind of average satisfied? Okay, so one other important development was, Gundermala, looking in particular at a lot of empirical data, noted that the conjectures, in general, these Cohen-Leinster type conjectures, Cohen-Martinet, for the p part, seem off when Q is replaced by a field containing pth roots of unity. All right. And so that also raises some ambiguity about p equals 2, because Q, of course, it does have second roots of unity. So maybe that makes too bad, or maybe somehow, I mean, of course, everything has second roots of unity. So maybe they're not extra roots of unity. All right. So what I'm interested in doing to kind of understand for different kinds of fields which parts of the class group behave in this uniform way and which have different behavior is that I want to prove theorems about these averages. Okay, I should say at this point, this would be like totally hopeless plan because without, incredible new ideas right now to prove, say, any other of these moments predicted by the Cohen-Leinster heuristics, it seems beyond reach. But I want to prove theorems about the averages when Q is replaced by a function field over a finite field, FQT. So let me just say a little bit about that. I know that some of you have thought plenty about function fields, but maybe not everyone has. So I'll just say, we're used to thinking about number theory and the arithmetic as being about the integers sitting inside of the rational numbers, and there's a sort of a very analogous number theory that is about the ring of polynomials with coefficients in a finite field and its fraction field, the rational functions. And there's absolutely nothing lost in my talk if you want to take, this FQ to be a prime field. So you could just think about rational functions with coefficients in Z mod PZ. Oh, except you shouldn't call it. Let me make it L, because it's not going to. We really don't want it to be the same P. That is going to be important. Okay, and so these fields of rational functions, number theoretically, they are a lot like the rational numbers. So there's a very strong analogy here. And one great thing about this analogy is that this is one field, but this is actually lots of fields, right? There's one for every Q. Okay, so there are a lot of fields here, and they're all supposed to be like the rational numbers, every single one of them. And then there is a thing that you can do here, which is you can let Q go to infinity. All right? So if you're studying these, you have a parameter that you can let go to infinity, and you can prove theorems that are like theorem, and they involve Q going to infinity. And if these are all supposed to be like this, there's still some real information there. But there's no analog of letting this little Q go to infinity here. So it's somehow a place where you can make a statement and prove it where there's no, which can be a step towards a proof for an individual Q where there's no analogous statement in the number field case. Okay. Yeah. What? Oh, well, I was just saying, okay, this should be e.g. For example, Q is a power of a prime. Yes, but if your favorite finite field is Z mod LZ, then you can let Q be L. But otherwise, if you like them all, you can let it be any power of any prime. Okay, sorry. Okay, so besides this nice trick of there being some possibility of letting a little Q go to infinity, the thing that really makes considering the function field case vastly more accessible is that there is this geometric side to the entire story. So for example here, even talking about cubic extensions, I said there's a lot of mystery about which primes should be good and bad. And so I'll stick to this. You think about a cubic extension. So this function field, why it's called a function field is because it's actually the function field of a space. It's a function field of the projective line over FQ, and a cubic extension exactly corresponds to a curve with a generically 3-to-1 map, a degree 3 map. So this is a curve over the finite field. So K, a cubic extension, corresponds to a curve with a degree 3 map to the line. And what does that look like? Right? So say down here, this was like FQ of T. This extension, what's one way to build a cubic extension? Well, you could take the cube root of something, right? You could adjoin the cube root of, say, something in here like I said t to the 7th plus te plus 1. Okay, so that's some way to make a cubic extension. Another way to write this, this is just formally, I could write it as adjoining some u and then taking the quotient by, I'll write it this way, the relation that u cubed should equal t to the 7th plus t plus 1. I'm writing it a little sloppily here so that just to make clear what the geometry is. This is an equation in two variables, t and u. So you would expect, right, it's one equation, two variables, it defines a curve. And for any point, for any value of t here, you plug in a value of t, you get 3 u values. So what you're seeing here in this picture is like this curve in the ut plane mapping down to the t line. All right. So, okay. So now here, when we want to take the discriminant, so we'll take now the norm of the discriminant, say, of our extension. And so this norm of the discriminant, so that's how we're going to measure extensions, just by the discriminant. But now the discriminant, it lies in this field. So let's take its norm, and now we get an actual positive number here. And for any x, there are only finitely many fields of discriminant at most x. But all the discriminants are powers of q. And where the geometry really comes in is that given an exponent for the discriminant, the k above, so the k whose discriminant has norm q to the n, are essentially the fq points of a moduli space of curves. So each individual k corresponded to a curve, and one nice thing about a set of curves is that if it's a reasonably natural set, it's not just a set, but it has an algebrogeometric structure. It's actually a moduli space. And so we can put all these k's together somewhere nice where they live together. They live together in this moduli space. And so and maybe I'll say a little bit more at the end about this, and sort of, I'll just say similarly for the class groups. So this question about these class group averages, they're about a big fraction. In the numerator, you've got sort of k with a class group element, and in the denominator, you've got k. All right, so it's sort of two counting problems. One in the numerator, where you've got k in a class group element, and one in the denominator, where you've got k. And so for both of these counting problems, the one that's sort of in the numerator and one that's in the denominator, the things that you're counting are close to being points, of a space that has some geometric structure. And so I think that the idea, as far as I know, the idea for using this structure to try to understand something about the function field analogs of Cohen-Lindster heuristics and things like this, it goes back to an unpublished manuscript of JKU. And then Jeff Ochter in 2006 was really the first person to prove a serious theorem. So he proved in 2006 kind of the first, I'll just say sort of Q goes to infinity. So I'll just say a sort of a Q goes to infinity theorem for for quadratic for, class groups of quadratic extensions. So we think that these kinds of conjectures, they would be true when you replace the rationals with FQT for any q, and little q doesn't go anywhere. Just any little q, those conjectures should be true. But we can't prove them for a single fixed q, just like we can't prove them for the rationals. But the sort of intermediate kind of theorem that can be proven is a theorem when q goes to infinity, that they're true. And then there is some subtlety that's actually really changes the difficulty of the problem in when and where exactly q goes to infinity. So the reason that there's an issue is that there's something else going to infinity, which was that the discriminants were going to infinity. Here the discriminants are q to the n, so that n is also going to infinity. And there's an enormous technical difference between letting q go to infinity before n and q going to infinity after n. All right, but I don't want to get, I'll say a little bit more about that. But the easier thing to do is to let q go to infinity first. And this first theorem of Jeff Octor, that's what he did. But then recently, there's been a huge sort of boost to this method and this approach, this work of Ellenberg, Venkatesh, and Westerlund, that they, let me say, I mean, I'll just say they then can let n go to infinity, then q go to infinity. It sounds like a minor thing, but it's actually just a huge, huge advance in the technology of using the geometry and the shapes of these moduli spaces to say something about the counting problem. And I'll tell you just a little bit more about why it's a big advance. If q goes to infinity right away, so before n goes to infinity, in the problem, which already had this limit as n, which is here the exponent of our discriminant, is going to infinity, then what it reduces to, then this reduces to a question about the components of the moduli spaces. Okay? So, in fact, you have to know very little of their geometry or their topology. You just need to know, okay, their spaces, how many components do they have? Whereas in the work of Ellenberg, Venkatesh, and Westerlund that I mentioned, where you let n go to infinity, then q go to infinity, you have to know much more detailed information about the topology of these spaces, not just their components, their H0, but you need to know about their H1 and their H2 and their H3. And so so their big advance came from proving stable homology theorems on these spaces, so that they actually are really starting to understand the shapes of these moduli spaces, which then through the Groth and Lefschetz fixed point theorem tell them about how many FQ points they have. Okay, so what I've been doing, and I should say that this is sort of work in progress, is to try to think about this question of good versus bad primes, on the question above. It seemed at first to me for this, it was fine to let q go to infinity first and do the easier thing, though we'll get into some subtleties that come up. But it's actually about, it's actually a question of components that are sort of unstable. So on question above, so about unstable components. Okay, so I'm not going to say too much about what I mean by unstable components. So it's a question of components, but it's sort of orthogonal to this work in that this work is about, in some sort of stable range, understanding all the homology. And I'm asking not to understand all the homology of these spaces of curves, but just their components, but in a range where even knowing the components is unstable. So basically, that's just shorthand for like the part that we don't understand as well. Okay, so let me give a theorem. So I'll just start with sort of an example theorem, even in this case of cubic fields that we've been talking about. Here, I'm just erasing these, of course, these many time changed guesses about 2 and 3, what's good, what's bad. Okay, so, okay. All right, so here is the theorem in. Okay, so given in, we're going to write C in Q for the set of totally real. So they're going to be cubics, but I'll just say what I mean by totally real is split completely at infinity. Okay, so I'm going to let C and Q be the set of totally real cubic extensions of FQT. So cubic fields in this function field sense, or cubic extensions of FQT. So so given a prime P, so what the analog of Cohen-Leinster would be about would be taking the limit as n goes to infinity of class group averages here. And before that limit, I'm sneaking in this limit as Q goes to infinity. But as Q goes to infinity, it's going to have to do a couple of things. First of all, it needs to stay relatively prime to P. My prime, I'm going to be asking about the P part of the class group. Otherwise, things behave very strangely, and no one understands them at all. Okay, and the other thing is Q Q minus 1 should stay relatively prime to P, I'll say here, for P odd. Okay, so if Q had to be relatively prime to P, I certainly couldn't ask Q minus 1 to be relatively prime to 2. Or then this is a kind of silly limit over the empty set. So I'll only require it for P odd. And the reason that I'm requiring this is I mentioned this observation of Mala that once you start having pth roots of unity, things are changing. And when P divides Q minus 1, this field, FQ of T, it has pth roots of unity. So I said these FQT, they were supposed to be all like the rationals. But they're not all quite like the rationals because sometimes they have roots of unity that the rationals don't. Yes?
Is Q a prime power? No.
Yes. Yeah. So Q is a prime power. But yes, I mean, it's also true if you only wanted to restrict to primes. The limit would be true if you want to restrict just to primes. But it's true also for all prime powers. Okay, and so now I'm going to write it in this funny way. I'm going to write it as if it were conditional probability just to remind us, I'm taking K to be one of these, oh wait, I didn't use N. Totally real, split completely, oh sorry, I needed to say in here. The N, there was a reason for the N, with the norm of the discriminant of K over F QT equals Q to the N, okay? So Q is for the base field, n is measuring the size of the discriminant. And if I average over, that's now a finite set. Okay, so I average over this finite set, then I'm going to let q go to infinity, then I'm going to let n go to infinity. And this is always 1 plus 1 over p squared, which, is it still on the board? Is the Cohen-Lenstra or the Cohen-Martinet conjecture for good primes. So maybe all primes are good. I mean, so this now is a theorem that sees something about the function field setting that is about this first moment here that looks like all the primes, the 2-part, the 3-part, the 5-part, they all follow this pattern, but then the story, it's actually more complicated than this for two different kinds of reasons. So first, okay, so for p equals 2, well, here, maybe first let me say for p not equals to 2. Okay. So that's the first moment. Okay, so for the, let's say, the next moment, so same conditions on q as above here. Now, let's say I take the next moment. So the next moment here looks like 1 plus 1 over p plus 1 over p squared plus 1 over p to the 4th. I should say these aren't mysterious, what they actually are. It's just I'm saying them in a simpler language that makes them seem more complicated. If you, instead of talking about the size of this group, you count maps from it to another group, and then you get sort of nicer answers. So these aren't mysterious, what they turn out to be. And they're uniform in this way, 1 plus 1 over p plus 1 over p squared plus 1 over p to the 4th for all. So this here is for p greater than 3, but for p equals 2, here you get, I'm going to write it this way, 2 over 2 to the 4th. So you get something different here. And this is sort of, at this point, the kind of correction that we expected, given Mahler's work, and I think was explicitly predicted that this average should be corrected like this by Derek Garton, that this is the sort of correction that you would need for roots of unity. So the fact that there are sort of the second roots of unity in the fields, which there certainly are in the rational numbers, and there are in these function fields, that is something that you just don't see at the first moment, but you see it in higher moments, and you'll see it in all higher moments, a sort of correction coming from the fact. So here, 2 is behaving not the same as, the last term here is a little different, and that's coming from the fact that there are second roots of unity in the base field.
So then
yes?
still ask 2q minus 1 is 1? You run only over characteristic 2 here, or you remove that condition?
No, I mean, you can't require q minus 1 to be.
But what about if
What?
you do 2?
What?
What about you can do 2 squared, 2 cubed, you could go over this tower. It would make, no, because you want q equal 1.
Yeah. So I have to.
You remove that condition.
So I only ever require this condition for p odd, just because otherwise there's an empty set, so you can't.
So you always ask, yes.
Yeah.
You always ask
Yes.
unity, as opposed to you never.
Yes. And I should say that if you instead instead of saying that you don't have pth roots of unity, if you require that instead that p divides q minus 1, then you will get a p here, and it will look like this. So it's still sort of uniform in a way that only depends on the roots of unity of your base field. So it's not too badly behaved. But it looked here, and I should say that this, for all higher moments, you have a similar thing. So I have a theorem for all higher moments where for all p at least 3, you've got a polynomial here that is satisfied and p equals 2 is off. But it's off in a way that any other p would be off as soon as it divided q minus 1, so you got p roots of unity. So I have to say this kind of surprised me, because even though I had been told by a couple of people that they thought 3 was good, I never thought that 3 was good. I don't know. Some of you maybe have thought about this question, so I was very surprised. And then I recognize that there's something a little subtle going on here, and it's one of the costs of letting q go to infinity. So let me just say here, okay, if I have a discriminant of a cubic extension, what does it look like? Okay, yeah, especially because a q is going to be relatively, I should have said q. Well, okay, let's just imagine it's okay. So if I have a discriminant of a cubic extension, it's going to be a product, right? If this were in the number field case, it's going to be some primes appear to the first power if they're just partially ramified, and then you've got the totally ramified primes that appear squared. And the same thing happens in the function field case, except primes are now irreducible polynomials. So you've got some partially ramified, okay, and some totally ramified. Okay. And now, so if let's say, I'm going to write C and Q prime. So C and Q here were my cubic extensions with discriminant q to the n, be the same extensions. Maybe I'll just write it's a subset of C and Q with this discriminant not square free. All right, so that is just saying now I want to throw out the square free discriminant things. So you have to have at least one prime that's totally ramified. Okay, now if you do that, so first of all, let's just imagine you had a bunch of numbers and you throw out the square free ones. You expect that to be if they were really the numbers, then you all know that's a positive proportion of things you threw out. You still have a positive proportion. The fact that when you do this with cubic extensions of even a function field, so for extensions of a function field, the square-free discriminant ones, it's a theorem of Daskovsky and Wright, then that's a positive proportion, but it's not 1. So you've got a positive proportion square-free and a positive proportion not square-free. But the trouble is that when q goes to infinity, when this base field, this little q, when that is going to infinity, the proportion of square-free things becomes 1. So that's a great exercise. You can just check that as a statement about square-free polynomials. All right? So if you look at square-free polynomials, and the proportion over fqt of square-free polynomials, as q goes to infinity, that proportion becomes 1. So when q goes to infinity, we're not seeing all of the k's. We're only seeing the ones of square-free discriminant. And I have to say that I personally never thought that would matter, because I thought, well, okay, whatever, that's not really have anything to do with the class group. But sort of continuing on here, so this limit here, where we still got the same kind of limit, if we now take the average of the 3 part and we force k to not have square-free discriminant. So So as q goes to infinity, we don't see any of these fields, because as q goes to infinity, as little q goes to infinity, the square-free discriminant things become 100%. If we do that, we get 1 plus 1/3 here, not 1 plus 1/9. So the square-free discriminant things average 1 plus 1/9, but the non-square-free discriminants have more 3 torsion in their class groups. And I should say that as little q goes to infinity, this is actually only seeing things that have a single totally ramified prime. All right? So the more totally ramified primes you have, actually the more and more this number becomes. So you could prove a sort of analogous statement where you kind of force more and more your number to be less, more and more, farther and farther away from square-free by having more and more ramified primes. And then the average of the 3 torsion in the class groups of those cubic fields is getting bigger and bigger. And I should say that, and so part of this is that, part of what's happening here is that when you count cubic fields and you order them by discriminant, you really see things with, see a lot less of the things where there's total ramification. The fact that those primes are appearing squared in your discriminant pushes those farther and farther. So as it's getting close to time, maybe I'll just say this in words, that if instead of ordering your k's by discriminant, you ordered them by the product of the ramified primes. So you just said, oh, I'll just take this discriminant and get rid of all these 2's, and I ordered them by the product of the ramified primes, then in fact, the average of the 3 torsion would be infinite. Because there become, as you allow more and more ramified primes, there's more and more 3 torsion. Okay, so maybe the takeaway, okay. Yeah, okay, I'll just say that in a second. So this is about cubic extensions, and so for that it's specific to 3. And we'll close by saying what has to do with 5. So, okay, but just the takeaway here. It seems that there's more 3 torsion in cubic extensions when, more totally ramified primes. So in particular, looking at the behavior of the 3-part on the square-free discriminant, cubic extensions is not, is not representative of what's going on. I should say up to these constants, sort of up to these constants. So just for concreteness, I stuck to the case of S3, but in fact, I have analogs of these theorems for general, actually I would say for general Galois groups, but I'll just say specifically for degree in Sn extensions. And the rough story is that p equals 2 sort of needs the roots of unity correction, as you would expect, and otherwise p dividing n are bad, and the rest of the p are good, in the sense that there's a polynomial in p and 1 over p such that all the other p's have those averages in this sense, where I took the limit as n goes to infinity, and then the limit as q goes to infinity, and then the limit as n goes to infinity. One thing that I particularly thought was interesting here is there is this recent great work of Wei Ho and Ela Varma and Arul Shankar, where they, in an infinite family, see something about the 2-part of Sn extensions for n odd. And I always wondered, like, oh, why can't they get n even? And now I understand that it's a different kind of phenomena for n even, because they're sort of bad in this other way, that the moments seem to be bigger than how the other prime's behaving. All right, thank you. Yeah.
So in the case of cubic extensions,
Yes.
in the QN plane in the first quadrant,
Yeah.
there are many ways you can go to infinity.
Yes.
Like, for example, Q and N could be approximately equal to 10 to the 10.
Yes. Okay, so somehow, all right, so the desired direction, of course, is for Q to be constant and N going to infinity. That is the desired direction to go to infinity, which we can't do anything now. And somehow when you get this, you get sort of for free, actually, I guess, some leeway in that as long as Q is going to infinity. I mean, if you just worked out the interior of the proof, you automatically could make some statement where as long as Q and N were going to infinity, where Q was a lot bigger than N, it would be okay. And then if you wanted to kind of break down the angles, it would be like, well, if you knew about not just the components, but about the H1, the first homology of these spaces, then you could like let Q go to infinity slightly slower compared to N. And the more and more you sort of the deeper and deeper you know into the topology of these spaces, there are more and more homology groups, you would eventually sort of approach being able to fix Q and let N go to infinity. Does that answer? Yeah, I mean, well, there's a sort of baseline conjecture, I would say, like the vanishing conjecture. So in this second paper of Ellenberg, Venkatesh, Westerlin. But again, I would say that's sort of still a baseline conjecture, and one would want to, it might need some corrections, but it is a sort of place to start, yeah. Yes. Yes. Yeah.
So you said they only need the information on the stable homology.
Yes.
So you're saying you're also trying to find something about the unstable part?
Yeah, so well, so I'm trying to understand sort of unstable components. Eventually, if you wanted to have this kind of theorem where you don't let Q go to infinity, you're going to need to know about sort of all the cohomology, so, stable and unstable and, but components and higher homology. Yeah, I mean, there's this sort of mix. In the end, it's an analytic problem. Some of the stuff somewhere can be pushed into the error term, and you only need to bound,
I was wondering if they give you information when you fix Q eventually and just let M go to infinity, would you need all the unstable information?
Yes, absolutely. So, I mean, eventually, if for, say, you wanted to understand class groups of cubic extensions, you will need to know, I mean, into the main term, there are going to be contributions from what you'd consider unstable components and unstable cohomology. But I think that unstable is a little bit of a funny term because sort of in some sense, stable is like what we understood at the first pass, and unstable was just like the stuff that we didn't understand at the first pass. So it's actually much better behaved. It has its own regularity. It's just not technically homological stability. So, yeah. Okay,
yes.
Christian. Yeah.
So your concept, I mean,
Yes.
on the analytic side,
Yeah.
Your concept of badness and goodness
Yeah.
is an average concept.
Yes.
But say for quadratic fields,
Yes.
it's funny because the situation, at least insofar as what we know is concerned, is reversed. If you look at
Yes.
exactly.
Yes.
If you look at particular quadratic extensions, and we know how we have a pretty good bound
Yes.
for the two torsion coming from genus theory, and for three torsion we're at a bit of a loss. We have some bounds, but they are far from what we think is the truth. And then for higher torsion, goodness knows what. Now, what do you think is the reality? Are the good primes become bad ones and vice versa? Or is it just that we know very little about the situation for individual quadratic extensions or individual extensions in general over what have you, the Q over function or other function fields when we don't have genus here.
Yeah, so I think, so summarizing a little bit, right? So it's funny to call, for quadratic extensions, the two-part bad and the odd part's good, because the two-part is the part that we understand. And the other part, but those are related. I mean, in that the one sort of way to understand the Cohen-Lindster heuristics is that it's a model of some kind of random object where everything is kind of random, and then there's lots of somehow cancellation, but there's extra structure on the two-part. And the extra structure both means that we can understand it better, but it also means that it doesn't have this behavior that it looks like a just sort of totally random thing. But if these parts that look totally random, it seems like somehow necessarily are going to be harder to understand.
Sure. But
So, yeah.
what sense do people have? I'm asking honestly, I do not know. About how bad, I mean, of course, we're far from knowing that, but how bad can individual quadratic extensions be as far as p-torsion go? So the general feeling is that it should be bounded by q to the epsilon, but that's pretty bad at this scale of things.
Yeah.
So should there be an infinity bound that is much worse than the bound for the bad primes, which we understand fairly well, or should it be about as bad? I do not know. And should it be should
okay.
models be robust when it comes to an infinity norm?
Yeah. So the okay. So maybe let me answer that. You can sort of actually see that in here. You have to sort of rephrase it in a different way. So how you're saying what's going to infinity, but what you can see in theorems that you can prove still with q is going to infinity, but theorems that you can prove on the function field side say that even for the bad primes, the worst that you're seeing are powers of log. Okay, so in terms of this, like how big could it be? D to the epsilon. So this would completely support what you see here on components. Completely supports the conjecture that the worst anything should be is d to the epsilon. And that's what you're seeing on average here.
Support for better things?
What?
From the function field. Is there any hope of proving or even having some heuristic evidence for something better than Italy?
For good primes. Yeah. You mean point-wise?
Point-wise.
That's a good question. I don't know for sure, but my suspicion is no. But one could look into that more carefully and see. Yeah.
So it's
good.
Very hard.
Yeah.
And it might not even be true, in the sense that it might not be able to do much better than the epsilon.
Yeah. I would, if I had to put my money on it now, I would say that there's not, point-wise, there isn't something better that's true even for good primes.
So I think, is there another question?
Yes.
Oh, okay, real quick.
I'm trying to understand the unstable range.
Yeah.
This theorem here with the square freeze allowed, that's the stable range?
Oh, you mean when I'm using these words stable and unstable?
Yeah, does unstable range refer to allowing ramified?
No, yeah. So that was just me. So all the work here, I completely swept under the rug. I mean, I didn't describe any of the work, and it's in understanding the components of these spaces. And that was just sort of as a black box. There was this work of Ellenberg, Wegentesch, and Westerlund that understood very well some of the components, which I'll just call as a black box the stable components. But then, and they in fact even understood the higher homology of those components to some degree. But then there are other ones. So I didn't describe it all because I didn't really describe the space except to say it exists. I didn't say which were the stable and which were the unstable ones or what that means at all. So I apologize, but yeah. Okay.
In the number field set,
Yes.
We don't know how to get second moments for the two parts of the class number for cubic extensions?
That's correct.
So we haven't seen this phenomena in the number field set.
Right. And, in fact, it would be a good thing to do. I mean, one should look empirically. I mean, this is, I'm just working on this now, but, even in the data, I would expect to see this These averages converge empirically better than asking about the probability you get a particular group, and I would expect that you might be able to see this phenomenon already in the averages, yeah.